Hello. Thank you all for being here again. And I want to continue where we left off yesterday, which was talking about this cartoon of a neutrino telescope. And today we're going to actually move to see how these detectors operate. But I want to talk about this last important component, which is this issue of the muon ranges and the tau ranges, right? So how far away does my mu neutrino or does my tau neutrino need to interact so that they can be seen by instrumented volume? So in the case of the tau neutrino, this is relatively simple. This is just the lifetime of the tau. This is actually a good approximation for most scenarios. It turns out that tau energy losses are relatively small, so you can assume that the tau is just going to fly through until it decays. So you have to fix it by the boost factor and then just the distance at the decay length in the lab frames. But the muon range is complicated. So now in this formula, now you can see that this now has some meaning. This is the inelasticity of the interaction that we talked yesterday. And this is the muon energy that comes out of my neutrino interaction points. OK, so we're going to talk about this thing here. So let's talk about energy losses first. So there are going to be essentially three important energy loss processes that are going to be relevant for our discussion. And they're going to be the dominant energy losses. So let's talk about them briefly. So Bremsstrahlung, somebody knows what Bremsstrahlung is? Probably many people do. So it's like radiation being emitted by the lepton. So you have a muon here, right? And that muon essentially emits a hard photon. Of course, it needs to recoil with a nucleus for this to make sense. So that's what I mean by Bremsstrahlung. So per production, also to be clear, in that case, what you have is you can do it in many ways, but for example, you could do something like this to a box, or you could directly just emit it from the muon, like that, right? In any case, not simultaneously, because then you have 4, right? But you can produce a pair of electrons. And then photonuclear interactions. So that means essentially you have a muon, and then I have my nucleon. By nucleon, I mean proton or neutron. And then it has a photon interaction. But this photon here is actually going to be a relatively high Q² photon, right? So this is going to be a relatively deep interaction with my quarks in reality. So this is really a quark-like exchange. Okay, so we have Brem, we have pair production, and then we have photonuclear interactions. Interestingly, the photonuclear interactions, so this thing here, these interactions are controlled by the same structure functions that, or similar structure functions that those that control neutrino nucleus interactions. Okay. So the energy losses, so how much energy is lost by unit of column density. So here X is column density. Okay, is going to be given by this relationship, where there are going to be 4 types, the 3 dominant types that I talked about earlier, and then there's this first one, which is ionization. And what's important is that all of these energy losses here, per production, Bremsstrahlung, and photonuclear effects, they're actually going to be to first order linear on the energy of the muon. And that means that I can rewrite this as some coefficient that is only logarithmically dependent on the energy of the muon, and then something that depends linearly on the energy of the muon. Okay? So in most of the times, you will see that to first order the average dEdx, so this should be the average ddx is given by this equation here. So it's A plus BE. And so most of the time, we just think this as essentially almost energy independent to first order. Okay. And, oops, no. And in ice, similarly in water, you have that the A and B coefficients are given by those numbers, which tell you how much you lose by ionization and how much is the sometimes known as radiative losses, so the B term. Okay. So can somebody tell me from this equation at what energy more or less the radiative losses, so the terms proportional to B and terms proportional to A, at what energy are those comparable? From that, somebody? Order of magnitude? How will you do that? Okay, we have to be able to do this because there is one equation, there are two variables here. And this is an algebra question. So I know people know the answer, but there is a high level of shyness going on here. About a TV, right? So thank you. So about a TV, they're going to be comparable. So namely, when A is more or less B times E, right? And so if you look at the values of A and B, that means that because there is this 10 to the minus 3 number here, that means that somewhere around a TeV is when the radiative energy losses are going to be dominant. And below, the ionizing energy losses are going to be dominant. So for muon energies below a TeV, more or less, I can think that the muon energy loss is approximately equal to a constant. So in that energy range, how does the muon length depend on the muon energy? This should also be easy. Well, this should just be, you guys are too shy. That the muon energy depends just linearly on the energy on the distance traversed, right? So there is a linear relationship between the muon length and the muon energy. Namely, if I have 100 GeV muon, then I can figure out that it should go. So if I measure the length that the muon traverses, I can convert more or less to a one-to-one correspondence to the energy that the muon travels. So that's really important, right? So that means that if I have a low energy muon below a TeV, measuring the muon length is equivalent to measuring the muon energy. However, when the muon energy is greater than a TeV, then the energy loss, looks now like this. And obviously, this no longer has a linear solution. The solution to this equation is this equation like that, right? So that means that the muon energy and the length that it traverses is not logarithmically dependent, okay? And so that has two implications. One is that measuring the energy length is not going to be a good proxy for the muon energy because typically those are going to be several kilometers of length. And then the muon length is not going to grow essentially in an unbounded fashion, right? So if you have a muon that has 10 TeV of energy, maybe it goes a handful of kilometers, and then from that on it can grow, logarithmically. But we are never going to have a muon that goes like 1,000,000 kilometers, right? Because of this logarithmic behavior. Okay. Questions on this discussion? No? We good? Yeah.
Those constants, A and B, depend on energy too, right?
Yeah, so these are approximately constant, so they really are energy dependent, but they depend like on the first decimal point on energy. So, and they also material dependent. In fact, there is a different dependence on the materials of each of these processes. Thank you. So this is how it looks in reality. So here we have the energy of the muon, right? And this is the energy loss. So this is a plot of this. And here I was telling you, this is the ionization loss. This is approximately constant. This is a log scale here. And these are the energy losses proportional to these processes. So you can see that the dominant process, so first of all, as we discussed, somewhere around a TeV, they cross. Okay. And then, so above a TeV, the energy losses are going to be dominated by per production and Bremsstrahlung with a subdominant contribution from photonuclear processes. Okay, so what about taus? So like I was mentioning earlier, the taus energy losses are going to be less. In most of the times, they're just going to decay promptly. So here we have energy again. So this is in, now notice that this is in MeVs. So a GeV is over here, and a TeV is here. So you can see that a TeV, my muons are going on the orders of 10 to the 5 centimeters, so about a kilometer in length. And then they can go tens of kilometers, right? So we see this logarithmic behavior in the muon length. Now the taus, like I was saying, the taus, energy losses are negligible. So you see that the distance that the tau travels is just linear. This is just the boost factor, right? It's just kinematics. Then eventually you see here, this starts to like turn. This is just because eventually the tau lives enough that it really starts losing energy. And when that happens, that logarithmic behavior turns on. But in most of the energy range that we care about, all the way up to, let's say, an EV, this is fine. Okay, good. So now we're going to put together our discussion from today and yesterday into figuring out the rate in which we can detect neutrinos with this box light detector. So the number of events that we are going to estimate in a given neutrino detector is going to be a quantity, which we're going to define as the effective area, times the flux of neutrinos. So that's the number of neutrinos that go through my detector per unit area, per unit time, per unit energy, per direction. So that's going to be equal. So this thing here is going to be equal to the detector acceptance to muons times the probability that a neutrino converts to a muon in the vicinity of my detector. Okay? And what is the probability that a neutrino converts to a muon in the vicinity of my detector? That is the ratio of how long the muon travels, so the distance it has to reach, divided by the neutrino interaction length. Okay? So that is the muon range, so that's the distance that my muon will reach my detector, times this quantity, which you computed yesterday. This is the neutrino interaction, the inverse of the neutrino interaction length, n times sigma. Now, I can rewrite this, and so this is about 10 to the minus 6 if you put the energy in units of TeVs. So it's a relatively small number. So then, the neutrino effective area, we call it, it's this probability, which is this number, times the probability that the neutrino survives. Remember that if the neutrino is less than, say, 50 TeV, then Earth is approximately transparent. But later you have to take into account that suppression, which is flavor dependent. And then this is your geometrical muon acceptance area. So you end up with a plot like that, where you have here the energy of the neutrinos in TeV. So first you have this linear behavior that scales like e to the 2.2. Why do you have this linear behavior? Because remember, at relatively low energies, the neutrino cross-section is proportional to a neutrino energy, so you get a factor of E, and the muon distance also grows with energy, so you get a double growth with energy. But then eventually it flattens, and it flattens for two reasons. The muon length now grows only logarithmically with the muon energy. And second, the neutrino cross-section also eventually stops growing linearly. It slows down its growth because there is this q-square dependence in the propagator that suppresses things, right? So this transition happens somewhere at the TeV. And this behavior only depends on the neutrino cross-section and the muon range. These are parameters that are fixed by nature, right? I cannot change these parameters. I can move this, this probability conversion is given by physics. Now, my detector size, the muon collection area, that I can choose. That's my parameter I can change. But these parameters, I cannot. So your number of events is going to be given by this area, which is my muon collection area times this thing here. Okay, so 100 TeV is a number that we like to use in neutrino astrophysics because in muons neutrinos is a transition between atmospheric neutrinos and astrophysical neutrinos. So we like to quote the area around there. So if we talk about first generation neutrino telescopes like Amanda or Antares at 100 TeVs, we're talking about somewhere on the orders of 1 to 5 meters square. And for ice cube, we're talking about the order of 100. This could be lower or higher depending on the efficiency or purity of my sample. And so the effective area of a neutrino telescope is the size of my telescope. This sounds trivial, but what do I mean by this? It means that it's the area that you would have if you were to have a comparable gamma ray telescope, right? A gamma ray telescope is, when a gamma ray hits a telescope, it sees a telescope. When a neutrino goes through ice cube, it most of the time just goes through ice cube. Okay, so if you have to rescale by the neutrino interaction probability, it gives you the area that 100% of your neutrinos would hit. And so ice cube is about a 10-meter gamma ray telescope right now. It's the largest one we have. And that is comparable to the Whipple telescope or gamma ray observatory in the 70s. And it's not surprising, this observatory was the one that saw the first diffuse gamma ray emission, right? And so ice cube, which is comparable in size to a gamma ray observatory, is able to see the first neutrino sources and the diffuse neutrino emission, right? So if you can think about gamma ray and neutrino astronomy are out of phase by 40, 50 years in terms of where gamma rays were and where neutrinos are. Now, you may say, well, if we are 50 years behind, what are we doing all of this, right? Well, the reason is that, like I mentioned earlier, there are two important facts. One of them is that neutrinos are able to probe, unimpeded for faraway distances. And second, and that's going to be important, we'll talk about this tomorrow, is that neutrinos have flavor. And flavor is going to be an important observable that is unique to neutrinos. Okay. So in reality, once you put cuts and whatnot, this is how the effective area of all sky looks for ice cube. This is the energy of the neutrino. This is the effective area in meters squared. And there are important features here that I want to talk about. First of all, there is this thing that says full sky. Full sky means integrated over all directions. Okay? So I every single direction. Northern hemisphere means goes through the Earth. You see here that the northern hemisphere nu mu is the largest of all the effective areas, followed by the full sky cascades. Okay, can somebody tell me why is the northern hemisphere nu mu larger than the full sky cascades? Or give me a guess of why that's the case. what's the difference between this new mu? Okay, so remember that cascades are events that are blob-like in my detector, okay? And tracks are these long muon ranges that go through my detector. Why will it be that this is much larger than that by a big chunk?
You are more sensitive to northern tracks than
Yes,
to full sky
good.
cascades.
So that's, go ahead.
The full sky cascades is like an average over the directions, maybe.
Okay, so the full sky cascade is, so I want to point two things here. First of all, the first thing you said is correct. The higher this line is, that means that you have more efficiency, right? So the higher the line, it means that we can see more events from that. The second point is related to your second comment, which is you were saying that, well, the full sky is all directions, and the northern sky is only one direction. Okay, but that's been added, right? That actually goes in the opposite direction, because in some sense, here I'm doing an integral over 4 pi, and here I'm doing an integral over only 2 pi. But still, even though I only do an integral of half the sky, this is higher than that one. So your second argument goes against it. Okay, so your first point was correct, but this doesn't quite explain it. Other ideas? So what's the difference between a track and a cascade? So the important part here is that the tracks, going to go back now to my diagram here, the tracks can be produced by things that reach out of my detector, okay? Whereas the cascades can only be produced by things that start in my detector. That means that the effective detector size for tracks is larger, right? The detector is effectively larger since things can come from out of it. That's not the case for cascades, but you have to start in within it. Okay, so that's the first thing we want to know this plot. Now, the other thing here is related to the other flavors. So the next thing I want to notice is this spike here. So this spike was because of this glass for resonance. This is because electron neutrinos, or electron antineutrinos, remember, when they hit electrons, they can produce their real Ws, and that enhances the neutrino interaction probability. That only happens for mu E cascades, okay? So you see that's only present in that particular flavor. The other ones seem featureless. And so the shape of these lines, you see that they all curve like this. This is because it depends on this cross-section, these ranges that are given by physics. Are there any questions on this figure? Is the physics of this figure clear for people? Okay. Okay, so now let me show you this figure here. Oh, there, question, good.
Yeah, so for the tau, we expect it to decay inside the detector.
Yeah, that's a good question. So
Yeah.
yes, that will be true. So most of these taus, they will decay inside because the tau decay length, typically, let's say 10 to the 7, so a TeV is here, this is 10 TeV. So a kilometer is here, right? So all the way until 10 PeVs, the taus will decay inside my detector. So a kilometer is here, right? So this is an MeV. So up to 10 to the 7, the tau decays inside. So if I go here, until this energy, the tau will decay inside. But here, in this energy here, the tau actually decays outside.
Okay, so that would be the thing that you showed yesterday, like the neutrino comes, decays into a tau, then the tau decays again into a neutrino. That will decay again into a tau inside the detector that will detect? No.
Yeah, so in that case, it would look like, let's say this is ice cube. So it will look like the neutrino comes in, the tau will hit here, and typically, in most of its energy range, it will decay instantaneously inside, but then it can come out. When the neutrino energy is greater than this, the tau will actually leave the detector, and you will not see it contained.
Okay, thank you.
However, the tau energy losses are much smaller, so it will look like a very dim track that comes out of it. That was a really, really good question. Thank you.
Sorry, I have another question.
Yeah.
I don't understand the effective area. I mean, for example, for a telescope in a certain direction, the effective area will be the size of the telescope.
Mm-hmm.
But if I wanted to calculate the effective area coming from another direction, wouldn't it be 0? I don't know.
Good, good. So let me repeat your question so we're on the same page. If I have a telescope and it's looking this way, and I ask you what's the effective area that way, is whatever the size is. And if I ask you what's the effective area through the ground, it's 0, right? Because you cannot see light through it. But this is the important part. Neutrinos actually go through the planet. Okay? So there is a chance that the neutrino is seen through the Earth. Okay, so neutrino detectors, unlike photodetectors, they can see neutrinos in all directions for relatively low energies. Now, you are right that eventually we eventually do get a shadowing behavior, and that segues to my next slide very, very nicely. Oops. So let's look at this. Here is the energy of the neutrino. Sorry, I keep changing my things from log to energy, but this is the neutrino energy. This is the effective area, and this is just for muons to make this simpler. But I think this is what you're asking. So these lines are given for different directions. Okay, where this angle is defined so that minus 90 degrees, this is declination, so minus 90 degrees in the case of ice cube. So if I have ice cube here, right, the Earth is like that. So this angle delta is measured like that. So delta of, sorry, not measured like that, not. This angle delta is measured like that. So that this is delta of minus 90, right? So delta of minus 90 is like your telescope, you're looking up into the sky, okay? And in that case, you see that it looks like the red line, like this. Now, if I look at this band here from 30 to 90 degrees, that means I'm looking from here to here. Let's say this band here. Now you're looking through the planet. And so now let's see what happens in this line. So you see, it's growing. And somewhere when you get to tens of TeVs, this is 10 TeV, it starts to bend. This bending here is exactly what you mean. It's the Earth blocking the neutrinos. In the case of a gamma ray telescope, you know, it's like a step function, you know. You cross it and you immediately don't see anything. In the case of the neutrinos, because the neutrinos can't go to the planet, it's a smoother function. Does that make sense? Yeah?
But then for you sum this or you average this?
Right, good. So when we talk about all sky, we mean all sky integrated. So it's integrated, not averaged. Okay, good. That's a good question. And so then there are things that are also interesting in these figures, which is related to why do they have different starting points for different directions. And that is related to the backgrounds, okay? if you look through the planet, so in the direction of the yellow, nothing but a neutrino can go through the planet, which means that anything that I see that shines light and is coming through the Earth must be a neutrino. That means that I can put a relatively low cut or very loose cuts in my event selection. On the other hand, if you see something that comes in this direction, it could be background. So I need to put higher requirements in those to be neutrinos. That is why this starts at higher energies. And we're going to talk about that more in some minutes. Okay, good. Okay, great. Are there any questions on this slide? Yeah. That's right. There are different directions in which the neutrino is incoming at the detector. Good. Okay. So now I want to be sure that we are all in the same page of how to use effective areas. Yeah. This one.
Just a neutral current interaction, or you are considering the track of the tau also? The effective area here. It's just a neutral current interaction of the tau. They're just a cascade.
Yeah, there is also a part of the new tau that produces charge current without a track. That's also included in that cascade effective
That
area.
is included also
Yeah.
in this.
Yeah. Good. Okay. So I want to do this exercise. So I want you to pair up with the person next to you. You can do it in pairs of three or triplets, I guess. And this is, so we are in the same page how to do this. So suppose that the effective area of a neutrino telescope is given by this formula. So it's 10 meters at 10 TeV, okay? And it scales like energy to a 0.8, which is what's given by muon ranges and cross sections. And assume that the neutrino flux is given by a power law, which is 10 to the minus 18 in these units at 100 TeVs. If I think about how many events all sky, and assume this is valid through the whole sky, how many events do you expect between this energy and this energy in 10 TeVs? So I'm going to give you, let's say, 5 minutes. This is a simple integral, or if you have a computer, this is even faster. So go and compute. Talk to the person next to you. Over 10 TeV. No, this is correct. I switch it up on you. Okay, do we have somebody with an answer? Or with an order of magnitude, at the very least? Not yet? People computing. Okay, somebody has a result? You do? You have an answer?
1.5.
One event? Okay. Other people have an answer? Is that the only answer? So how do you do it? Could you tell us what you do?
Just do the product of these two things, and integrated energy, multiply the flux for 4 pi and for all the time interval, and yeah, that's it. And integrating the range from 10 TeV to 10 PV, basically.
Yeah, so you have to do an integral, right? Yeah, so the tricky part, so I actually written this purposely like this because, and I hope I did this correctly, so now I'm going to see if I got the right numbers. But yes, so you will see that the effective areas, sometimes they're in digital format, but this is a very typical way in which people report fluxes. They report fluxes this is the flux at 100 TeV, and this would be given something like of this order. And then, you have to be careful because of the unit conversion business here. You're right, you have to do an integral. And I think, but my recollection is that maybe I forgot a factor of 10 somewhere. Now, where is my cursor? Oh. Cursor. Where is this? Let's see. Where is this? So now if I could find the thing that says larger. So this is the effective area that I give you. It's 10 meters, which I give you 10 meters, I converted it into centimeters square to match the units of the flux. And this is, I convert everything to GeVs to make everything in GeVs work. And then this is the flux. So this is 100 TeV, theta minus 2. And then you're right, you multiply by the time in seconds. So this is how many seconds are in 10 years, 4 pi, and then you do an integral. But I actually got 1,000 events, so maybe I'm not sure where you're off by 1 point. So I'm confused. But essentially, this is what you should be doing to get the event rate, okay? Good. So we are going to, so you should have gotten order 1,000 events for this flux. Good. So perhaps if anything is left of this lecture series, this is probably one of the most important exercises because one of your colleagues will tell you, my neutrino flux is this. This is what I computed for my theory calculations. And you're like, how many events should I see in IceCube? So you go to the IceCube website, and you will get this, but you will also get it tabulated per every direction. Okay, so you have a source. It could be NGC 1068, whatever you want. You want to know how many neutrinos we see. You need to be able to do these calculations. Okay, cool. So now, these events, this just tell you how many events hit our detector, and we select them. So the question is, how can we reconstruct these events? Let's talk about that. I will talk about it mainly in ice, but I will talk about water briefly. So this is an ice for water Cherenkov detector, right? So Cherenkov light is emitted by charged particles when they go faster than the speed of light in the medium. This is a cartoon of how that happens. It's essentially a coherent superposition of waves. And what matters is this Cherenkov angle. The Cherenkov angle depends on the refraction index of the material. And in the case of ice, it's going to be something of this order of magnitude, which means that it's going to be at 41 degrees. And it's, like that. Here we have a particle moving faster than the speed of medium in that medium, and you can see an equivalent representation. And I want you to appreciate that the ice cube logo, if you have never noticed, actually this is 41 degrees, is the Cherenkov angle of a muon. So that's nice, but this light is going to go through several actually hundreds of meters. Remember that this is going to be Ice Cube Neutrino Observatory, but these strings are separated about 100 meters and the dots about 70 meters. So it's a movie. You have a neutrino. It's coming along. It emits this Cherenkov ring, right? And then you see these photomultiplier tubes getting activated. And like I was mentioning yesterday, we represent the time of arrival of light by the color that is seen by color in these images. Let's play it again. So first you see these hits here. This is noise. This is noise mostly from thermal noise in the glass, for example. And so then it's actually the main hits. You can see that the muon losses are not uniform. So the number of photons lost is not the same as the trajectory goes through. This is not surprising. This muon is losing energy, right? So the energy loss, right, first is larger and it's decreasing. So there's more energy loss here and there. But also, the transparency of the material, in this case the ice, is changing as a function of depth. You can see that here in the middle, there is very little photons. This is because there is loss of dust in the middle of the Antarctic glacier. This is due to some geological effects. This is known as the dust layer. And so, okay. So ideally, these photons should make a nice 45-degree angle. So here I have another representation of my sensors. Here is the depth of my sensors in meters. This is the arrival time in nanoseconds of light. So this one here is the first sensor to see light in this event. And so now if I look at the sensors nearby, this is the, let's say, true direction. And that's how this sort of B-shaped cone looks like. So this muon, well, this is one-dimensional, right? But it gives you a sense of how we do the muon reconstruction. So if this is the most likely reconstructed direction, and if you're off by, say, 25 degrees, then you should have seen hits at a time where there are no hits here. Now, you also want to appreciate that there are these red dots here. These are late photons. These late photons are arriving late because sometimes a photon, not sometimes, very often, a photon is going through the ice, and it scatters with dust or an air bubble in the ice, and it bends. Okay, so when it bends, it no longer gets to you at the time that you would expect them to arrive. So the energy losses are dominated by these stochastic processes. So what is the implication of this? The implication of this is that the correlation between how much energy a muon loses in the detector and its muon energy is going to be very broad. So let me show you that in pictures. So if I have muon, okay, with 1 TeV. So this is a 1 TeV muon after 50 meters and then 1.5 kilometers. So you see this is the distribution of final energies. So after only 50 meters, the distribution of final energy looks like this exponential. But after a kilometer in water, in this case, it looks like this. Okay? So this is the same initial muon, okay? But it's losing energy in a different way in each of these attempts. That means that I cannot rely on the final energy loss to figure out the muon energy, because it's a very stochastic process. Is this slide clear for everybody? Okay. Okay. So this is how these muon tracks look to you. This is a low energy muon. This is to scale about 100 centimeter. This is 100 GeV. Okay. And this is a person compared to 100 GeV muon. And then this is a TeV muon energy loss compared to a person. Okay, let's see if we can move this forward. Oops, no, I wanted before. And so, oops, sorry. So this is a low energy muon at 2 different amplification sizes, from far away, closer, from far away, closer. Now I have a 1 TeV muon, far away, closer, okay? And if you have a 10 TeV muon, it has all of this structure here, right? All of this structure here is all of this pair production, this Bremsstrahlung radiation that's increasing, right? So the more high energy the muon, the more of these stochastic losses it has. Now, the light that you're going to observe in your detector is not only going to depend on these stochastic muon energy losses, but it's also going to depend on the absorption. And so the absorption is going to be depth dependent, at least in the case of ice cube, but it's similarly in water. So here you see the scattering coefficient, right? Or the absorption length in units of meters as a function of depth. So what does this plot imply? For example, if I'm about 2.2 kilometers deep in the ice, the absorption length is about 100 meters. That means that if I shine an LED light, you stand 1 block away from me, you should see that little light. So that's how transparent this is. Okay. If you are in this part here where there is more dust concentration, then you can only see light about 20 meters from the emission points. So when you have to reconstruct the particle properties, you have to take into account that the light yield is changing, even though both the muon is losing energy in a stochastic fashion, but also the number of photons that you receive in your detector are dependent on where those photons are emitted to. This is one of the most, or maybe actually the most naturally occurring transparent medium. Super Kamiokande, which is a neutrino experiment in Japan, has absorption lengths of the orders of 50s of meters, whereas in the ice you can get to hundreds of meters, right? So this is really very transparent. Okay. And then this is the other part, which is important, is the scattering length. So one thing is absorption. That means my photon is going through, and it gets captured, it dies. And the other thing is the scattering. My photon is going through, and then it sees a bubble, and it sort of bends or gets re-emitted. And so you can see that the scattering length is actually shorter than the absorption length in ice. So the scattering length typically is of orders of 30 meters. That means that a photon will bend 3 times before it disappears, on average, right? Good. So there's nothing as good as seeing this in video. So let me show you how this looks. This is a muon. So what you're seeing here is the individual photons going through or being emitted by this muon. And again, here the color means time. Okay, let me just play this again, this way. Oh, this was working fine. Huh, what did I do? Oh, no, that's good. So there you go. So every single hair here that you see is an individual photon that's just traveling. Remember that the separation between a string is 100 meters, right? It's a one city block, at least. Well, in Lima it's one city block, but not sure in most cities. But it's a macroscopical distance, right? Okay. See. Okay. Spend the final time. Oh.
How you know that the ice is stable? Because let's say if it's not frozen or frozen, and another question, how you know that is the ice is continuous, there's not bubbles?
Yeah, this is a real question, actually, Orlando. So the ice is the glacier is sliding slightly, so there is a shear motion. And then the issue of the bubbles. So most of the bubbles we are introducing ourselves by drilling in the ice. When we drill in the ice, we introduce bubbles. I'll talk about it in a minute. But the way we know the ice properties is because our sensors have not only photosensors, but they also have LEDs. So we can shine light in multiple directions, and that way we can characterize the ice properties. So we have measured that in situ, essentially. So the answer is we did not know, and there are bubbles. There are indeed bubbles. But how much bubbles there are, we measure through emitting light and receiving light ourselves. Good. So why is this a difficult problem? Well, this is another event. It's a muon. It's losing energy. It's emitting all these photons. And I want you to appreciate these circles here. Those are sensors that have seen photons, that. You can see how far away, the ones that are inside you cannot even see, but you can see these ones that are far away from the track of the muon, right? So this is a very difficult reconstruction problem, right? Because you have to take all of this information. By the way, so these circles means that one of our sensors saw something. Now, you could go and do this in a place where there is less scattering. And actually, water is less transparent, which means light travels less distances. But in that distance, it does not scatter as much. Okay. What's the advantage of ice? In ice, things go far away. It's very transparent, but things are diffuse. In water, things travel less, but at least they do not scatter. So this is the same muon, but now in water. So you can see now that the photons, are no longer doing this curly motion. They are now going in these sort of straight lines. Okay? So the reconstruction problem is much better. This is the reason why water Cherenkov detectors and upcoming neutrino water telescopes are expected to have better angular resolution than ice Cherenkov detectors. However, there are other difficulties. For example, in water, what Orlando was saying, the ice is sort of fixed for us in timescales of a neutrino interaction, or in timescales of order days, but in water, the detectors are moving around. Okay? So there are other difficulties you have to face, and so there are pros and there are cons. Okay? Good. So the way you resolve these events is you have some kind of like physical hypothesis. Yes. Oh yeah. Somebody. Who?
Between the first two illustrations?
Between which? So this one?
Between the first two.
This? Between this and that one? And this?
Between this and the next one.
Oh, between this and that one?
There was one, I think both of them was in the eyes, but there was one that looks like there is two peaks.
Oh, this one.
Yeah.
Yeah, so this is another muon. This one, you can clearly see the dust layer here. This is this part of the ice that is less transparent.
Okay.
This is this absorption that you have to take into account.
Okay, thank you.
Thanks. Okay. Okay, good. to switch that. So how we reconstruct this event, so traditionally, I will talk about machine learning later because I saw some machine learning people yesterday, so we will talk about that. But traditionally, you have some hypotheses. So for example, the interaction vertex of the particle, the direction, it's theta and phi, the energy in terms of arrival. And then what you try to do is you try to predict via some model that knows about muon physics, it knows about scattering absorption of light, try to predict the distribution of photons in each of your photomultiplier tubes, and then you fit that. Okay, so what we are fitting for is the time series of light in each of these sensors, and try to obtain these parameters in sort of a likelihood loss. Okay, and so how well we can do that? So this is the reconstruction. In the case of tracks, this is a recent paper by many collaborations, in fact. So this is the median angle between the muon and the neutrino. And here is, again, the neutrino energy in log scale. So you can see here, let's look at what says, well, all of these lines are ice cube, but there are different ice cube versions. But the best one is the blue one, or well, eventually the yellow. This one here is the resolution we can get. So at 10 TeV, it's about half a degree in ice. Now the black one is Antares, which is the water telescope that currently was stopped operating recently, but it's the latest one. And you can see that in water, the angular resolution is better, despite that Antares is about 1,000 times smaller than ice cube. So this is the tiny water detector, right? Ice cube outperforms Antares at high energies because it can contain the whole event. Antares is too small to really see the whole events at high energies. Now, another thing that we should be, we should note with respect to like gamma ray observatories is that we do not observe the neutrino directly. Yeah? You can never see the neutrino directly. You can only see the electron or the muon or the tau that's produced from the neutrino. So there's always going to be an angle between the muon and the neutrino that's going to be my kinematic. And so the mean angle between the muon and the neutrino is about 0.7 degrees at a TeV, and it, of course, because of the boost factor, it reduces itself with a power. So you can see that this is the position where the mean angle. So Antares is close to saturating the kinematic limitation of that. But at high energies, this falls faster, so we still have room to improve our reconstructions. Notice that in principle, you can do better on this, because if the event interacts inside the detector, if you were to interact inside the detector, so if the event is, oh, why did that change color? That's funny. If the event is true going, so if it's like this, so this is where my neutrino hits, then there is no way to improve beyond this error. However, if the neutrino interaction is like this, then in principle, because you also see the shower that comes here, you can use that information to reconstruct the direction. So you can improve over that for events that start in our detector. Is that clear for people? Okay. So now let's talk about losing the energy reconstruction. The energy reconstruction is given by the energy losses. So this is again one of the event displays. Shows you the energy loss function of time. And what's important is that we live in this regime, right, where the energy loss is proportional to the muon energy, right? So if I measure the energy loss, I can figure out the muon energy. Remember that we said earlier that muons of tens of TeVs can go several kilometers, which means that there is no way you can contain these muons in your detector, but you can measure the dEdx and figure out the muon energy, more or less. So this is the energy resolution is given in the logarithmic of the muon energy. So that means that if it says 0.3, that means that if I bin my energy in every decade in 3 bins, that's as good as you could do. So it's not even a linear scale, it's in a log scale. this is the muon energy at the entry point, and this is how well we can do depending on different methods. So why is this so bad? Well, it's for two reasons. Well, first of all, if the neutrino interacts outside of my detector, okay, like that, there is some energy loss here that there is no way I can figure this out because it interacted outside. So in that case, it's hopeless. Now, the other case is if the neutrino interacts inside of my detector, then yes, I can see this. But what I was saying is that the energy losses are stochastic, which means that there is a very rough correspondence between the energy loss and the neutrino loss. Yes, you have a question? Oh, this is based on simulation. Yes, based on simulation.
Like the difference between the true energy and the real one?
Yes, so the resolution is defined as the difference between the true energy and the inferred energy.
And then you take the log out of that.
Yes.
Okay, thank you.
So her question is just because she was on the microphone initially, is that if this is based on simulation, and the answer is yes, this is based on simulation. The direction, thank you for that question, because this is something that I had thought I was saying, but the direction is also based on simulation, but has been verified by looking at the moon shadow. Because the moon diminishes the amount of cosmic rays that are produced in that direction, we can infer the moon position, and that way we know that our reconstruction of muon direction is our right. Okay, so this is hard to improve for two reasons. One is an incomplete information problem. And second, remember that plot that's in yellow that I showed you earlier, between the final muon energy and the initial, for a given fixed muon energy, the muon energy losses is a stochastic process, right? So there's an intrinsic stochasticity that there is no way to go around it, right? So that variance in your muon losses, there is no way to go around it, essentially. Okay. So now let me talk about cascades, which is our other favorite morphology. So this is our muon. This is, of course, as you already know, it's a cartoon because photons go all over the place, but this is how we would like it to be. And then we have cascades. So this can be electromagnetic or hadronic cascades. Electromagnetic cascades emit Cherenkov lights. Hadronic cascades initiate eventually electromagnetic cascades, right? So in a hadronic cascade, there is a hadronic interaction that produces pions. Those pions eventually produce pi zeros, and those pi zeros decay into photons, right? So in an electromagnetic cascade, well, in a hadronic cascade, you have a hadron. Eventually, that hadron is going to produce pions. Okay. And then these pions are going to decay, making photons. And those photons are going to pair produce. Okay. So you're going to have pair splitting of those photons, making electrons. And those are going to emit Cherenkov light. Okay. So eventually, this produces photons. And then this emit Cherenkov light. If you have an electromagnetic cascade, then an electron is produced, and that can emit Cherenkov emission. The actual cascade, the hadronic or electromagnetic cascade, is typically small, of the orders of tens of meters. However, the light, as we were talking earlier, can go hundreds of meters, right? So the emission location is small relative to our detector sizes. And the emission of the light is approximately spherical, but it has a slight bias in the direction of the particle interaction. So how do these cascades look? So this is 100 centimeters, 100 centimeters. So this is 100 centimeters. This is a 10 GeV cascade, so maybe 30 centimeters in size. This is a 100 GeV cascade, maybe a couple of, not even, maybe half a meter or so. And this is a TeV cascade in size. Okay? So you have focused and very boosted. The cascade size are going to grow logarithmically with the energy of the cascade, right? So these cascades, as you can see, the size, even though it has grown by a factor of almost 1,000 in size, the size of the cascade has not grown significantly. This is because cascades are such that every population, the energy gets halved as the cascade developed, which produces a logarithmic length in the cascade energy. Okay. These are simulations, by the way. So how do they look in the transverse direction? If we were to look at those cascades in the other way, this is how an electromagnetic cascade looks if I'm looking at it face up. So it's very collimated. Hadronic cascade is more spiky. Okay, so let's look at how they look in the simulation. So this is a, what happened? Where's my cascade? That's weird. Is it, what happened? Huh. Okay, not nice. Where is it? So this is a cascade in ice. Okay. Again, you can see this sort of, let's see if I can place again. I cannot see where my cursor is. Oh, there. So remember, color is time, right? So red is earlier, blue is later. So it's moving towards the right. There's a slight asymmetry. It's going that way. Those photons are light slightly earlier than the other photons. But then there's all of this diffusion happening around it. And then we have, sorry, this should happen here. And then we have the cascades, in the water. And the other one was playing nicely, but. So this is cascade in water. And you can see now that the scattering is reduced, right? So there's more direct photons. Again, this is similar to what you were seeing in the case of tracks. We just replayed. Okay. Cool. Okay. We can go back here. Okay. So you can infer the cascade direction by looking at the time distribution of the photons at every sensor. So here is a cascade. Every sensor here has seen light. And this is a good example of how the reconstruction actually works in these detectors. Every panel here shows you the time distribution of photons in every photomultiplier tube. Okay, so the crosses are the time or a number of photons counted in bins of nanoseconds or so. And then what you see here are two lines. So the crosses are the data. The blue is the most likely direction, and the red is the opposite direction of orientation. And so you can see how the time distribution fits fairly well in the blue, but if you pick the opposite direction, it just predicts incorrect directions at everyone. So this is a very expensive reconstruction, you know. So are there any questions on this so far?
How is that fit made? You simulate it or?
The blue?
Yeah.
Okay, good. So what you do is you you have your detector. So let's say that this is a cube. So here are my sensors. Okay. So first you assume that it's going to interact here. And let's say that you take this direction here as my direction. And you say and you put some energy E in this point. Okay? So once I figure out that this is the interaction point and that's the direction, I run one of those simulations. And I ran that simulation many times with these same parameters because it's random. So now what I can do is I can obtain, for these photosensors, the average time distribution of photons in that one, after I do the simulation many, many times for that point. Okay, that's how I obtain one of those lines. Now if I can compute the likelihood with respect to data. And then if you want another direction, you do the same. You do many simulations for the same parameters, and then you figure out the line here, and you compare to data. Does that answer your question?
Yeah, so it's like really expensive to fit this?
Extremely expensive. So, a high energy event used to be, computational power used to be counted in grams of carbon. So it can take hours, if not even days, if a very complicated event is reconstructed for the high energy resolutions one, yeah. So one thing that we have now is you can do simulations of detailed photons, but you can have also tables that tell you approximately if you have a loss there and you're going this direction, more or less, we have like pre-simulated tables that we can use from other sets. Those is tricky. Those are average over the detector volume because remember that every part of the ice has different optical properties. So it's not the same to interact here or there. Okay, so you cannot produce tables that tell you, it's a high dimensional problem. You have to produce tables that tell you the light yield at every point in the detector at every direction with every energy. So that's very expensive. But we do have average tables, so we can do fast estimations. And then we can follow with data simulations. Now, this is one of the points where machine learning is very good at, because machine learning can learn that when you put a cascade here, more or less it should do these things in the nearby sensors. And you're going to see the improvement we get with that in some slides. But yeah, this is extremely computationally expensive process. Yeah, you have a question.
Hi. So you mentioned that with tracks, it's easier to estimate the direction of the mu1 than with cascades. But how about the energy reconstruction? It's easier in the cascades?
So the cascades energy reconstruction, that energy is calorimetrically measured. So the contained energy is measured with about 10–15% energy. That's good. However, so when you have a neutrino electron, for example, this is an electron here, a harmonic shower, I can measure the energy produced by this electron. So the energy of this plus that is known with about 15%. Okay. But there is no way that we can differentiate if what happened was this versus, for example, where this was a hadronic interaction. And so, yes, the energy deposited by these particles is known within 15%, but you cannot know if the interaction was a charge current or a neutral current interaction. And that makes a big difference, because if it was a neutral current interaction, some of the energy left the detector out of this neutrino, right? And if you remember from yesterday, the mean y, so the average in elasticity, is about 0.8, or well, depends on the energy, like of that order of magnitude, right? So that means that a significant fraction of the energy goes out here. Good. Great questions. And so now, this goes to Orlando's comment earlier, which is that there are air bubbles in the ice. But most of the air bubbles that are in the, or some of the air bubbles that are in the ice were actually put by us. So when we deploy the detector, this was actually a picture from Amanda, but similarly for Ice Cube. When we put detectors in the ice, we drill that hole that we saw in the first lecture, and then we put we put water back in there. That process, that water we put back in the ice has lots of bubbles. And those bubbles also distort the photon yields. So you can see this here. So this is a camera. This is the part of the ice that's refreezing. And this is a region with bubbles. That's why there is all this scattering. And this dark piece here is the untouched ice. Right? The photons just go there, never bounces back, so it's entirely black. So ideally, you would like everything to be dark in here. And so this is something as we know as the whole ice. So we have to, beyond modeling the ice layers, we have to model the rescattering of the light around the hole that we have introduced. And for that, what we do is we use these light sensors that we have in our domes. Okay. So how big are these effects? Well, they can be significant in how we reconstruct the light curve. And so this one is, for example, without these local effects, and then this is with the local effects. Okay, so that's the end point of this first part. And essentially, we have talked about particle injection, muon energy propagation, muon losses, and photon propagations. So it used to be that this could only be done within the collaborations, but recently we have put out this open source neutrino simulation that does all of the steps that I described for you. And so we call this Prometheus, and you can find it here, and it's described in this archive reference here. You can do all of these things that we described in this lecture in this open source package. So this is one of our Prometheus simulations. So in Prometheus, we have simulations for IceCube second generation. These are water detectors. This is, we haven't talked about it. We'll talk about this next generation detector. This is Baikal GBD in Russia. This P1 will happen in Canada. This Orca and Arca in the Mediterranean. And this thing here is called Trident. That's supposed to be the Chinese Neutrino Observatory. But if you go to our MC, you can not only simulate these detectors, you can design your own detector and do your own reconstructions if you want. So this is a nice figure of our Prometheus simulation and tells you, goes back to the question of the reconstruction that we had earlier. And what this tells you is how much computing time is used in the simulation for different steps. Like, for example, to simulate the neutrino interaction is called injection here. To simulate the muon losses is called lepton propagation. And then to simulate the photon traveling is called photon propagation here. And this is a stack histogram in log scale. So you can see that simulating the neutrino interaction is very cheap. It's of the orders of tens of seconds at best. Simulating the muon as the muon loses energy it travels, that's also relatively fast. It's the orders of hundreds of seconds. But then simulating all of those photons that are going into the ice or to the water, that is very expensive because there are millions and millions of photons, right? So that is very long. So you can play with that if you want. And then in Prometheus, we have simulated these detectors, and we have also computed effective areas using our simulations. And you can see, for example, this is our calculation of, for example, Orca, and this is the official one. And so we have, it works very well, is what I want to say here. Now, the other thing that has come into our field, which is, this is for an old conference, so that, is the issue of machine learning. So machine learning has become important because it's expensive to simulate all of these light photons, all of these photons. So how machine learning has been used in IceCube is, the problem is that IceCube has a non-regular geometry. The IceCube geometry is hexagonal and is sort of this weird shape. So how we've done it in IceCube, we have taken our detector and converted that into a 4-dimensional cube, where there is 3 dimensions in space and 1 dimension in time. And in these 4-dimensional cubes, we have a time series problem. Okay, so I have 2 minutes. Good. So this thing here is what we can do for, this is for cascades. which is the most tracks we can do better with traditional reconstruction, but cascades is better. So you can see here the difference between machine learning approaches that use exact parametrizations of, know the ice properties, let's say, from the simulation, versus standard likelihood constructions that approximate the light yields through the detector. And so the CNNs can get you to this much for cascade reconstruction. This is in degrees, by the way. And then this is for energy. So this is the traditional reconstruction, and this is the new machine learning thing. So this is really neat. Okay, so I have 5. Okay, then the other thing I want to show you is something that we are doing now with two of my students, which is another problem, which is, I think, interesting too. So most of the ice cube events look like this. It's like an empty box with some hits on it. And when you do a convolutional neural network, you do convolutions over your whole 4-dimensional image. However, if you do a convolution of this 4-dimensional image, the convolution is doing convolutions of most of the time just zeros, because most of these hits are just empty. Okay? And that's wasting a lot of time. So one thing that you can do is you can do sparse subconvolutions, sparse convolutions or sparse submanifold convolutions. And what you do is, instead of doing the convolutions throughout the 4-dimensional object, you define a submanifold that is defined as the hits that have points on it, and then do only the convolutions on those hits. So imagine that this is a 2-dimensional object. So this is my grid. This is really in 4 dimensions, right? Because there's 3 spatial dimensions, 1 time dimensions. And these are the PMTs that have seen hits in that representation. So in a traditional convolution, you will apply this kernel at every single point here, and then you will get something like that after you do a convolution. But if you do a sparse submanifold convolution, you only convolve the kernels that have seen hits, and you end up with something like that. And by doing that, you significantly reduce the number of convolutions. And so how is this effective? Well, this is the time of execution of the reconstruction. Performance is similar, by the way, as traditional, but this is the time of execution. These are different observatories. This is Ice Cube. This is the one in Russia, and this is the one in the Mediterranean. These are to be completed. This is the time of execution. This is for a this is for a track. This is the time of execution for a traditional reconstruction using a likelihood. We're talking about tens of hertz. If you use a CNN, you can get to almost a kilohertz in speed of reconstruction. And if you do our sparse submanifold reconstruction, you can do this with almost a speed of 10 kilohertz. And why is this important? These rates here, these histograms, corresponds to the trigger rate of our detector. So this is the number of events that we see in these detectors at every given time. And you can see Ice Cube typically sees about 3 kilohertz of rate. So you need to be able to reconstruct your events at this speed if you want to do real-time astronomy, for example. This is the case for Baikal, and then this is chemtrails. Okay. Another problem is, when you're trying to do these machine learning issues or machine learning techniques, is you have to operate these machine learning techniques in the South Pole or somewhere in the Lake Baikal in Russia or somewhere of the Mediterranean. And the problem is that power in the South Pole is very expensive. There is a power station that's fueled by jet fuel, right? So you cannot just have a huge GPU cluster operating there, right? Just burning fuel. This is just not going to work. So with one of my other students, Andy, we have been talking about how to fix this problem. And we have this solution here that uses something known as a TPU. This is known as a tensor processing unit. And this is a device that's about this size. And it actually is a low-power accelerator for machine learning. And to give you a sense of scale, if I were to reconstruct every single Ice Cube event with a GPU at real time, that will use about 18 households of power per day. So the equivalent energy of 18 houses. But if we actually use these TPUs, we think we can do it with only 1% of the energy. And so there is compromises to do this. The reason these TPUs are so much smaller is that these devices do not allow for float point operations. They only allow for integer operations. And so how do we do this? We have to take our events and we discretize it in images, and then we do essentially a simpler convolution. But this seems to work very well. And so I'm almost done for today. And I want to leave out with an, I think, hopefully inspirational slide. When I show this slide, people think I'm a little crazy, but I think it's I hope it's inspirational more than crazy. And it's like, if you think about, particle physics. So I always tell my students, like, there are three kind of particle physicists or physicists, or particle physicists. There are people that are very excited about theories and their theories, and they believe that if they just have that one theory, that's the thing that's going to make it work. And they're very theory-driven people. And then there are some people that are very data-driven people, that they look at the data sets and they see some weird correlation, and they're like, that correlation is going to end up being the Nobel Prize. If I follow that track, that's the thing that's going to make it for you. And then there are people that, find new technologies exciting. Maybe it's a new detector technology. Maybe it's like these new machines, whatever. Like that new technology is going to make it 100 times better, And really people are a combination of these things, right? They follow the data, you follow the theories, and you follow technology, and you balance these three things. But people are typically theory, data, or technology driven, right? Something is driving you toward the next step. And I'm very excited by technology. Well, I'm excited about many things, but technology is one of them. And one thing that I like is to think about what quantum computers can actually do for us in the next years. And this seems like very, very far away. It's not so far away as you may think like. So IBM now actually has quantum computers that have up to 120 qubits that you can use. Well, with grants and whatnot, but you can also use them publicly with up to order tens of qubits. So what we've been thinking with some of my students is, and some people in Spain, is how to do data analysis with quantum computers. And the problem is that quantum computers in the current era have only a finite number of qubits. And so the difficulty here is that you have to be able to store the information in a limited amount of qubits. And so we have an encoding protocol that uses the parity of the qubits to essentially store binary information. And we can store, for example, an IceCube event in about 8 qubits, and we can store all of Google Drive contents about 44 qubits with these things. And the problem is that this works on paper, but to make it actually work in reality is very difficult. There is this recent review that was written by, this is not me, by the way, it's another person. It was written by Snowmass, which is a US review process that talks about quantum computing in the high energy physics, that has many interesting ideas of how to use these machines for this is for high energy physics, but you will find something also for astrophysics and whatnot. And I like this figure that we made for our upcoming paper that shows you how we have been able as a society to use information more efficiently. And this is telling you the number of atoms that you need to store a byte as a function of technology. Right? So you have papyrus over here, paper, punch card, magnetic storage, optical disks, better optical disks, flash drives, solid state drives, and these sort of quantum qubits encoding systems. So you can see these sort of trends as we're going down, how much information we can handle, right? So when people say oh, we're going to do this surveys, we've seen so many stars and things, this is so much data, right? So maybe there's something here to think about. And with that note, I want to end today. And then tomorrow we're going to talk about just background and signal finally.
Thank you, Carlos. So we have time for one quick question. We are a bit late.
There's a question over there.
Hello, thank you very much for the talk. I have one comment and one question. So the comment is, I don't know if there is the IceCube collaboration, but in the kaggle.com, there is a website for data science and data sets. There is one open problem for an IceCube reconstruction, and they are pay $50,000 for the ones who can reconstruction using the data available on the data set. So there is a lot of teams work on that. And that's very interesting because Kaggle has scientific problems that are open for community for those who can solve that. So my question is, you said that you need to have these computational structures on the ice pole for identify the neutrino position. So why they need to be there?
Yeah. So first of all, thank you for mentioning the Kaggle challenge. The Kaggle challenge is one of our ice cube collaborators. It recently finished, so I think the awards have been given. But that doesn't mean you cannot try it. You can try it, and we'll hopefully do it again in a couple of years. So thank you for that. And then the other point is this issue of the speed, right? So there are two things that are important here. There is online reconstruction and selection, and there is offline reconstruction. So offline reconstruction means the events are recorded and selected, and then we think there are interesting events, and we ship them via satellite to the northern hemisphere, and then they get processed. When they get processed in the northern hemisphere, we can use massive GPU farms to process those events, and there is no limitations on that, essentially. However, detectors require to trigger on a specific event. You do not record every event that's observed in your detector. You only select the ones that look interesting. So the decision process of what is interesting has to happen on site. And that's why these sort of techniques are important. It's for the selection of the interesting events that you're going to ship to the north. And also, there is some applications for real-time astronomy that require speeds that do not have latency time. So this is both of these features. So yeah, thanks for that.
Thank you very much.